Since the dawn of time, humans have been fascinated with the stars. With endless limitations, the universe leaves us wondering, what's out there? We'll explore what is known and unknown in the field of astronomy. That and more on this edition of Equal Time. From the campus of San Jose State University, welcome to this edition of Equal Time. I'm your host, Journalism School Director Bob Rucker. Gravitational waves and the Big Bang, GPS tracking via satellites, and high-powered telescopes. There are several discoveries astronomy has had in recent years that have had a tremendous impact on what we can detect. Equal Time's Matthew Izak begins our coverage about what is known in our universe.
You're outside late one night. Look up, and you see the endless stars shimmering in the sky. Our universe is a vast, infinite space with much that is still left undiscovered, despite dedicated space centers.
I think among the sciences, astronomy is one of the more beautiful sciences, I will say. Just the pictures you can get from a telescope are just stunning. The colors and the shapes you can see in things out in space, but the magnitude, the things you're looking at are so big and far away and old, is just mind-boggling. One of the things they're studying is what makes the atmosphere of the sun so hot, because it gets up to 1,000,000 degrees in some places. Very sparse plasma, but very hot. The way I look at it is those are like heating coils extending out of the atmosphere and heating it up like an electric blanket.
We're in a heliocentric environment where the Earth rotates around the sun. And people might say, well, what's the difference? I see the sun going around the Earth, and one's the same as the other in terms of what I can understand.
100 years ago, Einstein came up with the theory of general relativity, which described the force of gravity being caused by the curvature of space and time. This was also a prediction of gravitational waves.
Einstein's picture of gravity was, imagine the Earth not exerting a force, but instead imagine it sitting on some fabric. We call that space-time, the fabric that it sits on. Now we've got this curved space-time. The curvature is caused by the Earth, and that's what general relativity says. And then it says an object in that curved space-time, like the moon, will just follow the shortest path it can through that space-time. And if the space-time is flat, that shortest path is always a line. But in this curved surface, it would be a circular orbit, sort of like that.
There's a significant real-world application for Einstein's theory. For example, the clocks and GPS satellites require a correction due to general relativity that allows our devices to be able to navigate us from street to street and around the block.
Imagine you've got a GPS satellite here, and you're at some position on Earth, and you measure through the timestamp how long it took the light to propagate to you. Then you would know how far away you are from that satellite. And by having enough signals from enough satellites, we can basically solve this puzzle of where on the Earth could we be, where we'd be on each of those spheres simultaneously. And that tells us where we are.
Asteroids striking our Earth have long been a fear of many, but the odds of that happening are extremely minuscule. Beiersdorf explains why.
In order for an actual collision to occur, the object needs to be traveling more or less directly at the Earth, so that it actually interacts with the atmosphere and gets slowed down and then crashes into Earth.
Nearly 80 years ago, a massive 2,700-pound meteorite was found in California, and its discovery was made possible by Chabot's education system.
What we have here is a plaster cast of the largest meteorite ever found in California. It was found up near Goose Lake in 1938. So the story goes there were 3 hunters from Oakland out hunting in the forest, and they ran across this odd-looking rock, and one of them recognized it as a meteorite because he had attended a public lecture by Chabot's second director, Earl Lindsley, about meteorites.
Now, when we come back, we'll look at what experts are doing to try and understand what we don't know about the endless skies. Welcome back. We've seen what we know about our universe, but there is far more out there that is still unknown. Theories have been devised and some even tested by astronomers who work to solve the biggest mysteries. Matthew Izak continues our coverage.
A significant advancement in astronomy began in the 1600s when Galileo invented the telescope. With these high-powered telescopes, the question remains, just how far can these see out into the sky?
You can see basically back to the beginning of time, basically, for the most part. That's not really controlled by the telescopes themselves. That's more controlled by just the way light works and how the universe works with the universe expanding.
So what shouldn't we do when operating a telescope?
You've got to be very careful about the sun. The sun can be very dangerous if you were to look through the telescope at a time when the telescope was pointed at the sun. And that's a good way to impair your vision.
Astronomer Paul Linham explains the technological advancements that are used at the Lick Observatory.
We have the capability and the intellect available here in Mount Hamilton to take advantage and exploit the new ideas and new discoveries of the early 1900s, including things like Einstein's general relativity. In fact, it was astronomers at Lick Observatory that brought general relativity to the United States. The advantage that we have, even though the telescope dates from the 1960s, the electronics and the camera and equipment on board the telescope we can routinely transpose and interchange as technology advances.
It's difficult for astronomers to fixate on one star because it is relatively empty in the night sky. Instead, they go about seeing these stars through a very specific process.
And we pioneered a technology here by using a laser, a giant laser that we mount to the telescope to inject radiation and energy into the atmosphere some 60 miles above the telescope. So we've basically injected energy into a spot of the atmosphere above the telescope, which then glows back at us.
The invention of the telescope has allowed us to capture images of the universe. However, there is a new innovation that could change what we know about astronomy.
There's sort of a second advancement going on right now, which is the development of gravitational wave detectors, which, like a telescope, is something that we can use to look at astrophysical sources and learn about our universe. But they do it by looking at something other than light. They look at gravitational ripples. That gravitational wave spectrum can tell us a huge amount of information beyond what we're able to get through just optical measurements and light measurements.
It is impossible to put in enough energy into an experiment to generate a detectable signal here on Earth. Instead, the limitations are broken through physics and what happens in the universe.
Nature has this laboratory all around us. It's the universe, right? And that's really the connection between astronomy and physics. There are experiments going on in the universe at extremely high energy levels where the differences between, for example, Newton's theory of gravitation and Einstein's theory of gravitation give wildly different predictions as to what will happen. And so if you want to probe those differences, you can look to the universe and let nature do the experiment for you, using things like black holes accelerating around each other and moving at near the speed of light.
While some experiments are not possible on Earth, others are coming to fruition. Some scholars are studying how we can improve travel here on Earth, but there are experts focusing on the vast unknown of our stars.
So black holes, they're exotic objects, but they actually work with, it's pretty simple, they work with gravity. So what happens is the typical way this happens is you get a very massive star, much more massive than our sun, and it reaches its end of its life, which they sort of live fast and they die young. Our sun lasts 10 billion years. These stars last, say, only 100 million years. And they grow really large, they explode, and the center of it will collapse during the explosion to form a black hole.
There's another type of black hole in each galaxy, one that is much larger than any other, but still relatively a mystery.
Another category of black holes we call the supermassive black holes. And this is the idea that the center of every galaxy, including our own Milky Way galaxy, has a black hole which is not the mass of a star. It's about 1,000,000 times the mass of a star, some of them even 1,000,000,000 times the mass of a star. We don't know where those come from. That's like one of the great mysteries in astronomy right now. There's a lot that's, the more we know, the more we realize we don't know. And what's interesting is finding out about the unknown unknowns, the things we didn't know. The reason we think there might be another planet is some patterns in the orbits of other things in the solar system, comets and things like that. And they're sort of lining up in a certain way that suggests that something is perturbing them, something's moving them around. And the theory is that there might be a large planet that's doing that.
Our solar system is only one microscopic portion of the fractal universe, and even all that we can see is still rather unknown. The evolution of technology and space centers propel our advancement in understanding the universe. Still, we may never know what's out there.
Now, when we come back, we'll sit down with experts, astronomers, and graduate students, all searching for solutions. Stay with us. Welcome back to this edition of Equal Time. Today our focus is on the new discoveries and the impact on astronomy. Let's meet our guests.
I'm Peter Beiersdorf, Associate Professor of Physics and Astronomy at San Jose State, and I've worked for the past 20 years or so on the design and development of gravitational wave detectors.
And my name's Aaron Romanowski. I'm Assistant Professor of Physics and Astronomy at San Jose State, and I work on galaxies, dark matter, and black holes.
My name is Maria Stone, and I'm a graduate student in physics and astronomy, and I work with Dr. Romanowski on galaxies as well.
And I'm Matthew Ziak, Senior Journalist Correspondent for this show on Equal Time.
Thank you all for being here today and joining us for this discussion. People at home are probably saying, well, wait a minute, is this about Star Wars or Star Trek, or is this pure science? How would we explain this to people, what you're talking about in terms of the new research, the new discoveries, Doctor?
Yeah, well, one of the big new discoveries was the detection of gravitational waves from black holes. And black holes are something that has been interesting to the public for some time. And it actually connects a little bit to Star Wars and Star Trek and things like that. Very recently, there was a movie, Interstellar, that featured a black hole as its sort of main character. And it's fascinating to see like real science and the types of things that we've been studying in classrooms and through equations come to life on the big screen and kind of engage the public in a way that classroom discussions and textbooks just can't.
And Hollywood and television are very good at bringing it home for people so they understand it. But Aaron, what is the difference between the depictions we see in images versus what's actually being studied?
Well, it depends on the movie or the TV show. Some of them take a lot of liberties. You can never get the science exactly right. Some of them are much closer to reality than others. Things like The Martian or things like Gravity or Interstellar. They're making some efforts to be as true to life as you can. And of course, for dramatic effect, you have to do things like put sounds in space sometimes and things like that. Some of them are pure fantasy. Star Wars, I love Star Wars. It's kind of pure fantasy. But to me, I was inspired growing up. Why am I an astronomer in the first place? Partly it was my dad took me to see Star Wars on opening weekend in 1977. And a little kid watching that, and I didn't understand the science in it, but I really got enthusiastic about space and gradually learned the science. So I think there's a real nice connection potentially between Hollywood and science.
Very good. And Maria, did this get you started in life, starting with the Hollywood and the creative and now into more non-fictional approaches?
Well, I want to kind of also state that a little bit to a side first that humanities and movies not always get inspired from science, but inspire science, because I think human thought went further in novels and sci fiction that maybe science got those ideas and tested them from there. So starting with Jules Verne from France. But yeah, I think I got excited about astronomy mostly from people who did astronomy, not from Hollywood. I didn't grow up in America, so. So
you have a different perspective.
Yeah.
When I was growing up, I was telling everyone earlier, in the 60s and 70s, we had the space program, and President Kennedy says we have to get to the moon, and then we're going to reach further. And since then, with your generation, how does your generation see space and space travel and exploration?
Yeah, I think it is a very glorified way of seeing it, because as you talked about, Hollywood does do some, over-exaggerating of the actual things that are happening out there, but at the same time, it sparks our interest, and sometimes it takes a little bit of exaggeration of something for people to get interested in it. Mm-hmm. And I think that, like you said, we've gone away from the informative things that NASA might be doing, that you really got to dig to find out, as opposed to it being headline news all the time. But Hollywood does a great job of at least introducing some of the ideas, and people go, wow, that's how that is. And then now you have documentaries and Netflix and anything that you could see on maybe A&E and that, and you start seeing that there's more and more coverage for the students and for just young people in general to get involved in this sort of thing.
Don't you love hearing young people talk like that about science and space and all that? But now, gentlemen, let's talk about your research. And what is the big discovery right now?
Well, the big news recently was the discovery of gravitational waves. These are things that people have looked for the past 100 years or so, ever since Einstein predicted them in 1916. So it's literally been a 100-year search. And just recently, February, they were announced that in September 14th, 2015, there was a discovery that two extremely massive black holes collided with each other and gave off more energy than the rest of the entire universe combined.
Wow.
For a brief period of time, a fraction of a second, and emitted these waves that traveled for a billion years before they reached the Earth. And we were fortunate enough to have detected those, and it gave us an insight into sort of what might go on in these very high energy extreme events. And it's given us a lot to think about what might be out there beyond sort of just the stars and planets and things that we can normally see using normal light and traditional means.
Very good. Gravitational waves. The audience may be wondering, what's the benefit for humanity? How will we harness this energy you talked about, or what's the goal?
Well, you never know. With pure science, it often starts off pure, and you don't get the benefits until much later. Nuclear power, for example, would have had its origins in very pure science. What was the reason for it at the time people studied it? So we just don't know until we start unpacking the implications of these discoveries. But partially, it's also just understanding our place in the universe, understanding where we fit in the cosmos. Sometimes there's dangers in the cosmos we need to know about, things like worrying about asteroid impacts, things like that. We need to make sure that they're out there and they're not out there.
I think Aaron hit on it perfectly because that's exactly what, as humans, we seek this sort of understanding of where we came from and who we are. And, there's religious plays a factor, science plays a factor. Everyone has this creationism, but there's a whole totality of where it all began. And, we talk about the Big Bang. And I know that there's some research going in to try and even replicate that over in Europe as well. I don't know if anyone has any thoughts on that, trying to re-replicate.
Oh, I think you might be talking about talking about particles that might make up the dark matter that maybe were formed in the Big Bang, something like that.
That is correct.
Yeah, so there's a lot of, I work on this area of dark matter. It's this great mystery that 80% of the matter in the universe seems to be some mysterious form we haven't discovered yet directly. We can tell that it's out there from its gravity pulling things around, but we just don't know what it is. It could be some kind of subatomic particle, like, you have electrons that are particles. It's something like that, but very hard to detect. So there's various theories out there what it might be, and this was a latest story from someplace in the UK that had another theory about that. But until we detect them in the lab, we're not really sure what they are.
It's interesting, though, that when you have something that you want to observe and see and some physics you want to explore, you sort of have two options. One is to try to create the conditions in the lab that produce this. So if you want to produce your own dark matter, you'd like to be able to crash particles into each other and generate some new particle or something like this. But you find that there's these limitations that we have here on Earth. I mean, there's only so much power you can put into these things that you're slamming together. There's only so much mass that you can collide. And it turns out nature has this great laboratory for us. It's our universe, right? And sometimes the things that we just can't do here on Earth, if we look out into the universe, we find these events that are just amazing and have energy levels and interesting physics going on that's beyond what we can do here on Earth, that allow us to test some of our earthly theories without having to build the experiments and find a way to do them, because nature has already done them for us.
Maria, we haven't heard from you about this concept of the history of science. We've had periods of time in human history where we saw science is debunked and we don't value it and it's anathema and all of that. And now we're getting into it. But are we getting into it in a substantive way? Are people learning really what they need to learn?
I think I got really inspired from Matthew's story, because when I got an invitation and I read on my email about you, Matthew, he's like, oh, I'm interested in astronomy, and I took 2 astronomy classes, and you're a journalism major. I'm like, wow, how did he take 2 astronomy classes? It was so exciting that somebody else who is not, just specializing in astronomy is interested in those questions, which people should. I think it's just so fascinating. The stars are right there every night. So, and we are curious. Dark matter is curious. So people, whether they're scientists or non-scientists, are scientists in some way in one part of their heart because they ask questions. So that's part of being a scientist. And basically, right now, astronomy is so great because a lot of the telescopes publish their data online. A lot of the scientists share their data online. So it's no longer like in a lab somewhere locked up under 7 keys, but it's really available for the public. And like Matthew, you, Bob, or anyone, even like my mom, they can go and access that data and make their own projects or do citizen science. I think that's what they call it. And they have online blogs and Twitters, and you can participate in that way.
And you don't always have to go down to the planetarium to study this. You have the internet available to you now. You have schools like ours at San Jose State that can trigger that energy, excite the mind, if you will.
Well, you should go to a planetarium. You should go to the California Science Academy planetarium because it's mind-blowing, big, and they have astronomy students for Berkeley, like doing the dictation. And I don't know, when I went there, it blew my mind, and I'm an astronomer. So.
Yeah, and some of the things that you learn about, things like astronomy, it crosses over because now we're looking at what Elon Musk was trying to do, was the whole Hyperloop and the whole idea of trying to travel at a much quicker speed. And I know, Peter, you might be able to elaborate a little bit on how that works.
Yeah, I mean, the goal would be to get from here to wherever you want to be in no time flat, right? And you might ask yourself, well, what are the limitations? Like, why can't we teleport? And I don't think teleportation is coming anytime soon, but we can certainly travel very fast. Our bodies don't care how fast we go. I mean, you have astronauts in orbit that are going all the way around the Earth every 90 minutes, and they can handle that just fine. The hard part is accelerating to the speeds that will do that. And so, the challenge of building something on the Earth to travel relatively short distances, like here to LA, you have to go around mountains. You have to go, where the terrain takes you, and those curves and the undulations are going to require accelerations to get the Hyperloop pod or the vehicle to sort of steer around those things. So, the body can handle about 3 Gs of acceleration without much problem. That's sort of what you might get at a wild amusement park ride. You might need a few more air sick bags in your pod, but you're going to come out of it okay. And that sort of limits then how fast you can go. If you can make a straight shot, if you could somehow tunnel and buy the land and do all that, you really could, travel here to LA in 5 or 10 minutes.
And I know you talked about limitations. I think that's the operative word. Limitations. I think this whole area of science with physics and astronomy does nothing but push limitations and push the boundaries. And maybe you can explain a little more about that, Aaron.
Oh, well, we're finding out how fast we can go, for example, in space. So there's new areas of propulsion that have been designed about using things like ions. It's rather than normal rockets, it's kind of emitting charged particles. Things like solar sails, or you could, or using lasers to propel spacecraft. There's all sorts of different innovative ideas out there that have been developed. So, the sky's still the limit, and a lot of could use young people with good ideas and lots of energy to go into these areas and find out, what the next generation can construct.
There's other limitations that come into play, and some pioneers who broke through those limitations. Back when the U.S. Air Force was interested in certifying flight restraints, so basically seat belts and harnesses for their pilots. This is 60, 70 years ago. They required that they be able to withstand 14 Gs of deceleration if there was some sort of crash or something. And they thought that this was sufficient because humans couldn't survive anything beyond that. And so they decided to do some tests to verify this. And this is when the first ever crash test dummy was created. Oscar 8-Ball was going to be this dummy fitted with all these sensors. And there was a doctor, Dr. John Paul Stapp, who was on site in the middle of, I believe it was Arizona, where they built this test track and this rocket-fired sled that's going to shoot this sled down to the end of the track, and then it's going to hit a lake, and it's just going to come slamming to a stop in a fraction of a second. And at that moment, there'd be this huge deceleration, and it would be equivalent to like a jet crashing or a fighter pilot ejecting from a seat. And the idea was to have Oscar 8-Ball, the crash test dummy, in the seat. And this doctor, John Paul Stapp, decided no, he was going to ride in the sled. He had his own ideas about how much deceleration the human body could take. And this was based on just sort of an intro-level biology class and an intro-level physics class that he had taken. But this was before the internet, and his superiors were 2,000 miles away. He was in the middle of the desert, and so he climbed in and he rode that sled. And he survived. They added a few more rockets to the sled. They accelerated faster and faster. They got well beyond the 14G barrier. Eventually, he got to a point where they fired the sled to near supersonic speeds. And he experienced more than 14 Gs just speeding up to maximum speed before the crash. And he stopped. He went from about 600 miles per hour to stopped in 1.1 seconds. And there were pilots flying overhead monitoring the status. There were all the alarms blaring, telling people to get out of the way because there's going to be this big crash. And the rescuers came up to inspect him, and they thought just sort of retrieve his body because they didn't think that there was any way that anybody could survive what turned out to be 35 Gs of deceleration. And he had survived. He broke nearly every bone in his body. His capillaries broke and his eyes filled with blood. But he went on to recover, lived a long, healthy life. He was at the White House when Ralph Nader was there to announce that seatbelts would be required in cars, much based on the work that he had done in the desert, sort of pushing the limits of human capabilities.
See, this is why space and science and astronomy is important, because you got us fired up, and I hope our audience was inspired as well. I want to thank you for joining us. Thank you for coming up with this topic. And we hope you'll come back for another edition of Equal Time.